First, let's welcome Professor Pandharipande, and who's going to speak about moduli spaces of holomorphic and meromorphic differentials.
Okay, so thanks for the invitation to speak here. I will attempt to give a Blackboard talk, so we'll see how that goes. So we start with C. So C is an algebraic curve or a Riemann surface, so it looks like this. It has some genus, and so we view this as a curve or a complex Riemann surface. And we will not study it just by itself. In fact, the very old way of studying Riemann surfaces is with a rational function. You can take a, maybe that's too small, C and F. So F is a pair. So F is some holomorphic map to P1, a rational function. And this perspective of studying curves is very old. It goes back, in fact, to papers of Riemann himself. And if you have such a function, then if I change dimensions, I have some picture where this is the P1, and my curve is some kind of branched cover. And this leads to a very explicit realization of the curve. If you know about these branch covers, it leads to relations to representation theory of the symmetric group. And there's a whole subject here, which is not what I'm talking about today. So this is maybe Hurwitz covers. So that's a very old way to think about Riemann surfaces. And if you think about this for a moment, you realize, well, there's many other things one can do. And the idea that will be mostly around this talk is rather than picking a function, you can take a curve and take a differential form. So this is a section of the canonical bundle. So you can view this as a holomorphic differential form or maybe a meromorphic differential form. And so by this I mean really a section, so it's a form, like that was a function. And if I take this data, it gives me a rather different way of looking at my Riemann surface. So it doesn't really give me a map. There we had a rational function. By the way, a rational function is a section of O. So this gives me a different way of looking at the Riemann surface, which is also old and well explored, although perhaps not back to the papers of Riemann, which is it gives this idea of a flat structure. On C, well, not quite C, C minus the set of zeros. Let's say it's a holomorphic. And how does this work? So here's my Riemann surface. And if I pick some point that's not a zero, then, so a Riemann surface, because it's a complex object, it has some charts. So around any point, I can find some kind of chart in the complex numbers. But since we have the additional data of this differential form, we can pick special charts that have the property that the differential of this chart is equal to the form in that neighborhood. We can always solve such an equation, and as long as this form is not zero here, this really gives me a local coordinate. And I can do this at other places. C, and then I can ask, well, how do these local coordinates differ? And if you think about this for a moment, there's a dz here and a dz hat. And the fact that both of these respect omega, it means that this exchange map is just shifting by a constant. So this is translation by constant. So this gives a flat structure on this curve minus the points. And this, you should view this as somehow analogous to this picture of the Hurwitz cover, which also gives a very concrete structure. And as I said, so there we had some connection to representation through the symmetric group. This is a subject that has also been developed. It's related, so people who study this, this is related to the polygons in the plane and billiards and Teichmuller dynamics. And maybe I give just one example because this picture is perhaps less familiar than the top one. So let's give an example in genus 2. So sorry, this chalk is... So here, if I can draw in the plane an octagon. See if I drew it correctly. And then I imagine that I identify these sides. And if I do this, I get a genus 2 surface. And it will have a differential form because there's the dz from the plane. And this gives a very concrete way of looking at it. For example, you can say a genus 2 surface, what are the Weierstrass points? And it turns out the Weierstrass points are the center point. Then there's the edges, the vertices. These vertices are all identified. So this is one Weierstrass point. That's the second one. We're missing 4 more. What are they? They're the midpoints of these edges. There's 4 edges here, and there's the midpoints. The ones on the other side are the same. So those are the 6 Weierstrass points of that genus 2 curve. So this is a way that's actually a very concrete way of looking at the curves. You might ask, well, am I really capturing the full moduli of genus 2 curves this way? And you can see, well, what was the moduli of this picture? Well, I picked these 4 vectors, v1, v2, v3, v4. Once you give me 4 vectors, I can build an octagon out of it. So the moduli in this drawing is 4 moduli parameters. And you could say, well, what is the moduli in the actual complex problem? Well, the complex problem here is a genus 2 curve. And what's distinguished is the point, the vertex point, which is the Weierstrass point. So it's a genus 2 curve with a Weierstrass point. This has moduli 3 parameters, 3 dimension of moduli. And so it looks like there's one off, but actually here, as I said, this problem is that problem, a curve with a holomorphic differential. And what the other one is that we're supposed to pick a holomorphic differential that has 0, that's twice that point, and I get the scale of the holomorphic differential, how big it is. I can multiply it by 17. So there's one more, 3 plus moduli plus 1, the scale of the differential. I'm not saying that this is isomorphic set. This is just part of it. But this method is kind of effective. OK, so this was the introduction. And of course, when you think about this, there's no reason to stop here. You can take the data of a curve with some k form. And this is from this line of reasoning, this is more or less all you can do. If you have a curve and you want to take some kind of bundle object on it, there's only the canonical bundle. And you can just take powers of it. That's more or less the only options you have. So this gives the presentation. All right, so now we come to these questions of moduli and some kind of ideas like Gromov-Witten theory. So let's start with the one that's better known, which is C and the rational function. If I want to make a moduli space out of that, then it's been known for a long time, and there's a picture there. The first thing you might consider is the moduli space of stable maps, say of degree d. So these are the moduli space of maps from the C to P1 of degree D. But this loses some data. We could have a finer moduli space. So here, in both cases, here it played a role. If I have this differential form, the zeros play a role, because the flat structure is only off of the zeros. In the top, when I have this rational function, it somehow ramification behavior plays a role, because outside of the ramification locus, it's an étale cover. So we might want to keep that. And the simplest way to keep that data is, so we want to keep the zero and pole data. And it's been well known for many years how to do this. Is there's a moduli space. Is that too low? So this, oh, maybe this just goes. There's a moduli space where I have the genus of the domain, and it's a map to P1. And instead of the D, I put a partition. I explain these symbols here. So this partition is a partition whose is a list of numbers: M1, M2, ML. And these numbers are allowed to be positive or negative. And I have their sum to be 0. So these can be, they could even be 0. The elements here could even be 0. It won't play a role. And so you can think about this as there's the positive parts and the negative parts. And I draw the picture of the Riemann surface mapping to P1. There's 0 in P1. There's infinity. And the ramification over 0 is the positive parts, and the ramification over infinity, say, is the negative parts. And that's why they have to sum to 0. And finally, what is this? It means that, well, this moduli space of stable maps, we should mod out by a certain scaling. And the scaling corresponds to the fact that we will consider more or less the same geometry, whether we take the rational function or 7 times the rational function. Okay? So this is a subject that goes back many years in Gromov-Witten theory. So there's the names here. Well, Yongbin Rawan introduced some of these ideas, and Jun Li, and then there's been a symplectic development also. When I have this moduli space, it maps to the moduli space of curves, where this L is the length of the partition. And it just maps by forgetting the map and remembering the curve with all these points. And you can ask, so one of the nice things about this space is it has a virtual cycle. It's a virtual fundamental class. And the dimension of this virtual fundamental class is given by deformation theory, or in fact, it's actually the classical dimension that in fact was even known to, if it goes too high, I won't be able to get it back, was known to Riemann, and the dimension of this, the cycle dimension, is 2g minus 3 plus the length of mu. And if I push forward this class, I can push it forward here. So this is push forward of that virtual class. This gives me a cycle class in the moduli space of curves, and the cycle class is of codimension, exactly codimension g, because the moduli space of curves has dimension exactly g more than that. And this cycle class is called this double ramification dr cycle. And it comes up in Gromov-Witten theory, and so there's a discussion of this that's very similar to what we're talking about in this talk, but actually it's not the subject of this talk. The subject of the talk is the analog in this case of the differential form, or higher differential form. But this is a theory that's also probably better known. Okay, so let's put this up. me try to get it down. Okay. So if we think now about what to do in the case of the holomorphic differential, the matter is not entirely straightforward in the sense that it's a subject that, I tried to present it in a way that one should view as a subject that Riemann himself could have been thinking about. It's just to take, instead of a curve in a rational function, a curve in a holomorphic differential. But it hasn't had as much development and from the point of view of study of moduli. But on the other hand, there has been a stream of activity. So I'd like to summarize a little bit of that now. So what about the moduli problem, C in a holomorphic differential? All right, so the first thing is that, like in this rational function, we will want to keep track of the data of the zeros or poles. So first of all, there's two things we can do. We can consider holomorphic ones or meromorphic ones. Of course, holomorphic ones are a special case of the meromorphic ones, but the behavior is slightly different. So we keep track of a partition. So mu, this is a partition of 2g minus 2. And this gives, so my partitions here can take negative numbers. So this gives me the data of the zero multiplicities and poles. All right, so just as before we had a partition of 0 because the trivial bundle has degree 0, now we have a partition of 2g minus 2. And it's the first step in considering the moduli is a very simple thing to do, which I can define a locus that depends on g and mu, and it lives inside mgn, so no bar. And a point here, this is equal to a curve with mark points, exactly n of them, distinct, such that if I take the divisor given by these mark points and twist it by the parts of mu, so let's put here mu. m1, m2, mn, and these are integers. As I said, you could put 0 if you want. It doesn't change very much, but you should think of them as being positive or negative, where positive are the zeros and negative are the poles. This is isomorphic to the canonical bundle. All right, so this is an easy step in defining the moduli of differentials. We are not interested in the scale. We weren't there. We're not now interested. I mean, one could, but we're not interested in the scale. If you have this differential, then it tells its whole story by its zeros and poles. And here we record the zeros and poles, and this gives a nice locus. And this is actually, it's a very beautiful locus. I think this is a fact that's not so well appreciated by algebraic geometers, but in fact, this is non-singular. It's one of the most basic aspects of the modular space of curves that this moduli problem is non-singular. But in fact, when I fix the zeros and poles, I look at this locus of differentials, it's actually non-singular. So this is, I said, this is a fact that's been known in different groups, but I think that in terms of actual algebraic geometry, a proof was written down by Polishchuk pretty recently. From the point of view of the flat surfaces, that community has also known it for a long time. But one interesting thing that happens immediately is that while it's non-singular, its dimension differs about whether you're in the holomorphic case or the meromorphic case. So the holomorphic case, this is when all the parts are positive or greater than or equal to 0. And the strictly meromorphic case is that there exists some part that's strictly negative. So, and the difference happens is that in the strictly holomorphic case, this is non-singular of codimension g minus 1. That's the codimension of this locus in here. It's non-singular codimension G minus 1. And in the strictly meromorphic case, it's of codimension G. They're different. And if you're an algebraic geometer, this difference is obvious. It's because the bundle of differentials is special. It has the H1. And if you gave it some poles, you've increased the degree, then it becomes non-special. But anyway, it comes out here, codimension G minus 1 and codimension G. So the world, when one studies these differentials, there's always a difference between this holomorphic and meromorphic world. It's by difference by 1. And I should say that if you're somehow playing this game somehow statistically, you expect codimension G. We found codimension G in this problem. In the problem, the analogous problem with rational functions, it's codimension exactly G. And how to think about that codimension G is that, well, you have these points moving on the curve. The fact that the linear combinations of the zeros will exactly equal the linear combination of the poles, which is what you need to be a rational function, the chance of that happening is kind of codimension G, because you need to have that to be a coincidence in the Jacobian. The Jacobian is dimension G. So you expect codimension G, and that expectation is satisfied in this Gromov-Witten case. And here it's satisfied in the meromorphic case, but it fails in the holomorphic case. And as I said, it fails because that the canonical bundle is special and has too many sections, exactly too many by 1. And that's why it fails. The interesting thing here is it's non-singular. This is really kind of this is really a special property. Okay, so, but we want to have a full theory which involves this virtual class and the cycles, and eventually compute it and answer many questions. And for that, we cannot restrict ourselves to studying the space inside this moduli space of non-singular curves. We have to confront the issue about what happens in the boundary. And so this subject, I would say, has been a bit neglected by algebraic geometers. Move this down. But this has been partially repaired since last summer. What happened? Oh, this one. This has been partially repaired since last summer, where there were 3 papers on this subject in the past year, and I want to say a little bit about them. Actually, before I say that, I will say something about some older ideas, which has to do with Wittens' R-spin theory, the R-spin class. So yeah, before I say what happened in the past year, let me say that there is another way to think about holomorphic differentials, and it comes up in a theory that Witten described in the 90s. And I want to say a little bit about it because it's actually very related, but it's not obviously related. So this is a theory about integration over a moduli problem, and the moduli problem is a moduli problem of a curve. And then we want to pick some line bundle L, and this line bundle should be an rth root of the canonical bundle. But this is very hard to be an rth root of the canonical bundle, because the canonical bundle has degree 2g minus 2, and it's not so often that it's divisible by r. Well, actually, exactly 1 over r at the time. But we'd like a theory that's somehow alive more often. And so the idea is we twist it. So here, to start this theory, we have an r, which is telling us what kind of root we're taking. And then we have some numbers. 0 to r minus 2. You can also add some more, but. And then the moduli problem is a curve together with an rth root of this twisted bundle. And this theory still has a problem to make sense. We need to have R divides 2G minus 2 minus the sum of the AI. This constraint still applies. And Wittens suggested for this theory the existence of a certain virtual class on the moduli space. There's this moduli space, these rth roots, and the data is genus, and then this vector. So there should be so Wittens suggested and constructed in genus 0 the existence of a virtual class and the integration of descendant classes against this, and the connection to this RKDV. So this is material from more or less 90s. So some people maybe remember those developments. And then there was a mathematical period of constructing this class and developing this theory. I don't summarize it now, but it's a kind of intricate theory to construct this class. It's somehow a more difficult class to construct than, for example, the virtual class here. So this is, the very first constructions. So it's been a long line. There's also by Polishuk, Weintraub, and then lots of people have constructed. And the theory has grown. It's now a special case of what's called this FJRW theory. Okay, so why do I talk about it here? Well, this really looks like something to do with the problem that I'm discussing, because we have here the differential forms, and here are some zeros. And in some sense, this thing should be somehow, in some way, connected to moduli of curves with differential forms. Although there's something puzzling because there's an R here. And then a very important calculation which I suggested there is one should think a little bit about where does this virtual class live. Well, this virtual class lives in this moduli space. I can push it forward, and this is a virtual class now in the moduli space of curves, and I can calculate its codimension. Then the codimension formula for it, so this is the codimension of that virtual class. Codimension, I write the formula here, and it is this. R minus 2, you can find this. We get the sign right, plus sum of the i's. So that's the codimension. When I take this R-spin class and push forward to the moduli of curves, it has a codimension. The codimension, of course, depends on G, R, and depends on everything. A, and this is now confusing from our perspective here because we expect something codimension G or maybe G minus 1. But you see, we have these AIs, and the step that is most parallel to the right-hand side is that we should maybe specify, in some sense, specify all the zeros. This is the condition sum of the AIs equals 2G minus 2. If I view this as an imposed zero, specify them all. And if I do that, something magical happens with this formula. So under the specialization, well, you can do it for yourself. The answer is G minus 1. So that's kind of good news. It's in predict is independent of the AIs. And if I look in the world on the right, it looks like it's in the holomorphic side, which is, in some sense, also, I'm making these. Well, anyway, so this is a theme that'll come back if I have time at the end. Oh, this one I want to go to the top. Okay, so about the progress in the past year. So one thing I want to say is that there's a very natural way to define a space. So here we have. So we look at these we look at these differentials, holomorphic or meromorphic. This is a space that's inside MGN. And there's a very natural way to consider a space, I put a tilde here, that's inside MGN bar. And this space was constructed in a paper with Gabi Farkas. This was last summer, more or less. And I wanted to say just a few words about this space. So this thing sits inside here, and this is compact in here, closed. And how the idea of this is a very simple idea. In fact, the idea is that if I take some general element of this space, it has some curve with some points, and these points are twisted by these M1, M2, Mn. And for this space, which is including degenerations, we have to see what happens to these curves, what happens to these points when the curve breaks. And the idea there is that there are some very simple, nice, sufficient conditions, which says that, well, when this breaks, some of the m's go here, some of the m's go here. This is guaranteed by the fact of how breaking happens in MGN. But the question is, what are the conditions now on these points? The wrong answer is that these points have to be a section of the dualizing sheaf of a nodal curve. I mean, this is a possibility that the dualizing sheaf of a nodal curve is certainly a well-defined thing, but this is the wrong answer. I mean, it doesn't have to. And the right answer is, well, it has to be that up to some twisting. You have to twist one by the way or the other. This is a very old idea. I mean, certainly when I was in graduate school, everybody was doing this. This is semi-stable reduction, and it's a very old idea in algebraic geometry, very simple. You just have to twist. You look at this line bundle, you twist. When you twist on one side by 5, you twist on the other side by -5, and then the condition is that these points on each curve, they have to be a whole meromorphic differential, and the meromorphic differential depends on how much you twist. You get a lot of chances. That's very simple. It becomes more tricky to describe these conditions when you have loops. But in fact, this is also not so hard to do. The idea here is you put these twisting numbers on every node and desingularize, and you should have a meromorphic differential on each one. And then finally, you have to write down some combinatorial constraints that these numbers satisfy. And there's just very simple rules. I don't explain them now here because it would take us some kind of time. But the nature of this space is just that the points in the boundary are these nodal curves with some points, and in order to be in the space, there has to exist some twisting rule that satisfies the conditions such that on every component it's a meromorphic differential. It's not very hard to write the whole thing out, but it's not maybe the right thing to do here. And this is not very deep in some sense. It's one of the very first things one would think about in this problem. But the thing that's interesting that happens there is that it's not the case that the closure of this space is that, which is to say these conditions I've described are sufficient conditions. They're not necessary conditions. They're necessary conditions. They're not sufficient conditions to be in the limit. So this space is bigger than the closure. So in fact, there's the open space. There is its closure. And then there's this bigger space. Okay? This is the situation. The analysis of who precisely is in this closure is a result of another paper, which is to say somehow once you've decided on this picture of these twists, you can ask which precise ones come as limits. An answer to that question has been given by Bainbridge, Dawei Chen, Gendron, Gruszewski, and Martin Muller. And they explain that if you want to really know precisely who's in the limit of a smooth point, then you have to look at these, and then you have to consider an array of residue conditions. Actually, the very natural conditions also. This is somehow not in the direction the talk I'm going in, but this question has also been answered. So one of the things that Gabi Farkas and I discovered about this space, so it has these extra pieces. And there's a question, what are those extra pieces? Why are they there? And it turns out that one of the things we prove is when in the meromorphic case, so mu meromorphic, but one can consider everything. But as I said, there's a difference between the holomorphic and meromorphic cases. And in the meromorphic case, this space, although it has these extraneous pieces, is of pure dimension, pure codimension. You can guess pure codimension G. It's of pure codimension G. So all the stuff that you're throwing in by just considering these natural twist conditions, you get other stuff, but it's of pure codimension G, which is exactly the codimension you expect. And moreover, there's a natural class, which is just a fundamental class. Actually, it has some weights, but I leave it here, that since it's pure codimension G, it has a natural class, which is just its fundamental class. This is a lot easier and better than what was happening in this space. I mean, I love this space, and Andre and I worked on this for a long time in some sense, but this space is complicated. If you look at its image in the moduli space of curves, it's a rather complicated space. It has kind of a virtual life. And what happens here, it's not true. That in the meromorphic case, this moduli space is just of the right dimension, so you can take its class. So it's just asking you this. So there comes very natural questions now, when in some sense this is the beginning. And in fact, in almost all math lectures, one tells the story backwards, so we'll get to the beginning later. Well, they're different. One is the closure, and one is the solution of those twist conditions. Okay, so a question then you can ask is, since this is a nice class of exactly the right dimension, you can ask, is there a formula? Okay, this is one question. And the feeling about this is this should be a little bit easier to approach than the closure, because the closure, well, this is some kind of almost Gromov-Witten object, so that theory is good for formulas. Second question you could ask is, well, if we found a formula for this, does this class determine the class of the closure? Because maybe one you like the closure. And the answer to this is yes. This is very simple. This is the subject of work. In fact, everything I say after now is all work with so Felix Janda, Aaron Pixton, and Dmitry Zvonkin. So the answer of this is yes, and it's not very hard, meaning that we know this space very well, and what you put in the boundary are some copies of these things that occur in lower. I could give some examples, but this is pretty easy, actually. This is an interesting question. Is there a formula for this? And the answer is conjecturally yes. So yes. Conjecture. And I want to now finish the talk with explaining this conjecture and why we think it's true. In fact, it's essentially proven, but to be honest, to say it's conjecture. And actually, that's the beginning of this, which is how this discussion in some sense started. And that's the formula due to Aaron Pixton. He wrote down a formula in 2014. And you can view this whole development as in some sense searching for the geometry behind that formula. And the answer, I'm going to give you the formula in a second. The answer, the geometry behind that formula, is exactly this class. So the reason that Aaron Pixton was writing these formulas and searching was he wanted to solve this problem. What is this class here in codimension G? This has to do with a problem that's called Ely-Ashberg's problem, and has also a history in the past 15 years in mathematics. And he proposed a solution for that, which we later proved. And but that solution, you could change the twist that was with this was a solution for rational functions, but you could also put in his formula, you could also put in holomorphic differentials or twice holomorphic differentials. And then we were wondering, you could ask yourself, what is the answer? What is the question that his formula is answering? And as I said, it's exactly that. So I wanted to end with, I have 10 minutes, right? It's 50-minute talk? What? Okay, good. There's the chalk. All right, so I want to explain the formula. So this formula is going to be a formula. This is a formula for a class, which I call P because it's a Pixton class. It's in codimension. It's a formula for all codimension D, and there's the genus, and then there's this mu. In this case, this mu is a partition of 2G minus 2. All right? So this is a class, and this class is going to be in the cohomology of the moduli space of curves. And we don't really know how to write down the full cohomology of the moduli space of curves. So if I'm going to write down a formula, it means I'm not going to really write down a formula in the full cohomology. The class is actually going to live in the tautological part. So in fact, it's going to be an algebraic cycle class, and it's going to live in what's called this tautological part of this cohomology. And what this means is that almost by definition, this class is going to have to be written as a sum over graphs. And these are stable graphs. And these stable graphs index the boundary strata of this moduli space. And more or less if you have actually a healthy class in the healthy tautological class, more or less the only way to express it is going to be a sum over the boundary strata because it could sample everything. Unless you're very lucky and most of the coefficients are 0. But roughly speaking, a healthy formula, you have to sum over the entire thing. So these are stable graphs. And so what's the data of a stable graph? Well, it has some genera, and it has some mark points. Well, the mark points correspond to the parts of mu. So these are the legs, and maybe have some loops. OK, so we want to have this. So Aaron writes the sum over stable graphs, and then he wants to have a second sum, and this is over weightings, or maybe admissible weightings. I explained this. And after that, there'll be stable graphs, weightings, and then there'll be some kind of summand. This is the formula. And the summand is going to factor in the standard way you expect these summands to factor, which is it'll be a product over leg, vertex, and edge terms. So it's actually quite a simple formula, except for one interesting thing, which is this weighting, which I will discuss now. So the weighting is a data. So I fix a graph. This is some stable graph in my sum. And a weighting is a map from the half edges of this graph to the set of integers. And this weighting, of course, has to satisfy properties. 3 properties is if I have a leg. So some half edges are legs. A half edge, in fact, is either a leg or half of an edge. But if the half edge is a leg, this h equals some ith leg, then this weight has to be equal to this mi plus 1. We've already assigned a number to every leg, which is this part of the partition. You might wonder about this 1, but this is a point of constant confusion about how you index it by how you indexed your holomorphic differential. We put a 1 here. And then for every edge in the edge set, well, this edge consists of 2 half edges. And then the next condition is there's a balancing condition. That when I have 2 half edges that actually make an edge, the sum of their weights would be 0. And the final condition is a vertex condition. And it says that when I sum over all the half edges incident to a vertex, and I sum over their weights, then this is equal to twice the genus of the vertex minus 2 plus the valence of the vertex. Okay, so anyway, these are some conditions, but we have a problem with this, is that if you look at this problem for a moment, you realize that there's infinitely many possible. If the graph has loops, then the number of weightings are infinite. This is not hard to see. Basically, after a loop, you get, oh. So we're going to have a problem summing over infinitely many things here, because this is always hard to sum over infinite many. You have to use convergence or something like that, and we're not doing that. So Aaron's idea for this is that there's a regularization of this sum. So the idea is to introduce a new parameter r. And yeah, we already saw parameter r in this talk. It's not exactly this parameter, but also it's not unrelated somehow. This is a different discussion. So this is some positive integer, which we'll later send to infinity in some sense. And when we look at our weightings mod r, and these weightings now, instead of going to every integer, they go to a much smaller set of integers, 1 to r minus 1, which exhausts the residue classes mod r. But these are actual integers. And then we have the same conditions. We insist on the same conditions, but we insist on these conditions mod r. Okay? So, what? H of gamma. This is the half edges of gamma. What? Yeah, sorry. It's the same there. And then we insist these conditions are satisfied, but mod r, right? And the idea is we're going to send, in some sense, we'll send first r. R will be, you think about r as something very large. And the one advantage of this, obvious advantage, is that there's only finitely many of these because there's only finitely many possibilities for this weighting. So the price you pay is something that depends on r. And then you look at admissible weightings mod r. And now this is a finite set. So we can write a formula, or I could say Aaron can write a formula. And that formula I now write. P d r g mu, the sum over all the stable graphs. This is the set of stable graphs. And then sum over all of these admissible weightings of this graph mod r. That's that set I described. And then in all of these sums, we have the automorphism of the graph. That's a number. And then a power of r. This is h1 of the graph. And then this graph defines some boundary elements. That's a push forward from the boundary element. And then there's a vertex term, product of all the vertices of this graph, the vertices of that graph. And there's a kappa class there. That's exponential of minus kappa of that vertex. So now there's just some classes. These are very well-known classes. That's a kappa class. Then there's a leg term. And for every leg, there's exponential of mi. That's the part of the partition and the cotangent line at that leg. And finally, there's the edge term, which is in some sense the most interesting. And this is the edge term. So edge is equal to 2 half edges. And what comes here depends on the weights at the half edges, which is 1 minus exponential. I hope I have enough space here. Minus the weight at the first edge, weight at the second edge. I'm sorry it gets a little small here, but all these formulas are in the papers. Then the sum of the cotangent lines, and then divided by the sum of the cotangent lines. 2 points. Okay, I'm sorry about that. It's not so readable. But that's the formula. It's not such a bad formula, actually. In fact, somehow there's a complexity here about summing over the admissible weightings. But the actual vertex, edge, and leg terms are rather simple terms. They're not so bad. And so the claim is that, so Pixton's claim is the first that we have to get rid of the r. The claim is that for r sufficiently large, this is polynomial in r. And if you want this without the r, the regularization, you calculate that polynomial, and you set r is equal to 0. This gives you a class without the r. So now r is gone, and we have this class. This d means, oh yeah, I should have said this takes the degree d part. You take the codimension D part of this. And so the final proposal is if I take the codimension G part of this, G mu, this is equal, so there's a factor of 2 here, minus 2 to the minus G is equal to this class that we defined. For the fundamental class. So this is the conjecture that links all of the parts of the story. It says that there's this formula that Pixton described, and it calculates the double ramification cycle in the k equals 0. This is the one twisted. It's a very explicit formula. And the answer is it actually calculates this class that comes in this paper with Gabi, this fundamental class. And from this formula, you can then calculate the classes of all those closures and somehow unwinds that. There's a lot of questions in this subject which I don't really have much time to answer. I'll make one comment about the nature of these taking the constants. I gave a talk similarly about the k equals 0 story in Bonn last year, and Don was in the audience. And these things are somehow related to Bernoulli numbers, but their exact production of the numbers from these graphs is there's some work to be done on how to do that. Of course, you can just do it, but closed formulas. And finally, let me say one more comment. I could say about why I said this is almost proven, but that's a separate thing, is that I mentioned this Witten-R-spin class. And another line of thought is connecting these ideas to that. And this results in a paper that will soon appear with Felix, Dimitri, and Aaron, is that we can prove there, using the study of the Frobenius manifold, that Witten-R-spin class is also polynomial in R. And if you take the constant term of that polynomial, which is somehow parallel to the story, if you take the constant term of that polynomial and you scale it appropriately, you will get also something related to this story, which is maybe I write it here. Yeah, so there's somehow R equals 0 limit of this Witten class, this Witten-R-spin class. There's a formula for that, conjectural formula, which gets the closure exactly, but only in the holomorphic case. So this is the second thread of this theory that ties together. Anyway, maybe I stop now before.
So we have time for a few questions.
Is this sum of the graphs an expansion of some exponential integral?
Yeah, I don't know what the answer to that question is. That's the reason. So he's saying that this thing looks like some expansion of some Feynman integral. And maybe you could make up an artificial one, but I don't know how exactly. But that's before you take this R equals 0. I don't know the answer to that question. I mean, in some sense, you can say where does this come? It comes as some vertex contribution. And maybe this is the answer. I don't know if you're happy with that. But these kind of things come as some vertex contribution of some orbifold Gromov-Witten theory. This is the question. Maybe also how is this proved in the cases it's proven? But there is an interplay with the orbit, some BZR that is related to this in Kyoto's formulas.
Well, when people studying entanglement entropy, they do orbifolds by cyclic groups and then take the limit when the order of the group goes to 0.
Yeah, sometimes that's somehow related to this. That is related, yeah.
Any more questions? Well, since we still have a little bit of time, maybe you can say, well, I have a question. Maybe you can say a bit more about the connection to Wittens-R-spin theory.
Yeah, so this was a question. I think Paolo Rossi posed us this question about is there a polynomiality in this Witten class? And the statement is that if you have to do it in the case that exactly I said, where the sum of the AIs is equal to 2G minus 2. Then I said that this Witten class always lives in codimension G minus 1. And the statement is if I take R to the G minus 1, I hope these constants are right. Maybe Dimitri will tell me what these constants are. If I take exactly this scale times this Witten class, this is this R class with G and these A1 to AN, that this is for large R, this is a polynomial, a cohomology-valued actual polynomial. And so then I can, well, so I think I need this normalization here, 1. And this polynomial, this is a polynomial. That's actually a little bit complicated to prove it's a polynomial. And we can only prove that in cohomology, not in Chow. Once it's a polynomial, I can set it to 0. This is a polynomial. I mean, the standard thing how this works is for sufficiently large R, it's a polynomial. You calculate that polynomial, then you set R equal to 0. And then the precise statement is that this is some cycle class. And in cohomology, the conjecture, its precise conjecture, is this is the class of the closure. And this is true in the holomorphic case because these AIs, they're actually positive numbers. These AIs. This is the holomorphic case. And this had the chance of being true because this class was codimension G minus 1, and that class was codimension G minus 1. And so this is not a theorem, but we've checked various cases, and we're probably further from proving that one than the other one. But maybe Dimitri has a different opinion about it. But yeah, this is a precise statement that intertwines. I mean, these spaces have these closures and these tildes, and their fates are intertwined somehow.
So thank you. I think we're ready for the second talk of the morning.